Okay, so today we're going to cover MCAT math. MCAT math is different from regular math because we haven't got a calculator, and there's some interesting things that you can do because this is a multiple choice test. So let's get into that. So the first thing is, if let's say that you have to multiply 6.84 times 2.25, right? And if this was a regular class, you would just punch that into your calculator. But we don't have a calculator. So how do we deal with numbers like this? Because you will still get numbers like this, and you have to be able to deal with it, even though you don't have a calculator. So one of the things that's really important and a skill that you're going to have to build up is estimating and rounding. Because estimating, it's not something that we normally have to do because we would just punch it into a calculator. But in this case, we have to learn how to estimate and we have to learn how to round. And estimating and rounding, if you estimate and round too much, you're going to get too far from the answer that you want. So you have to learn how to estimate and round smartly, right? Just how you had the idea of like the educated guess, not just blindly guessing, we have to round in an educated way. So how can we best round and approximate? So for example, we're dealing with this one, right? 6.84 times 2.25. Now, first of all, right, what we would love to do is just round this to whole numbers. And we could round this to like, 7, right? Or and like 2, right? I round 6.8 up because it's closer to 7 than it is to 6. I round 2.2 down because it's closer to 2 than it is to 3, right? And 7 times 2 will give me 14. Now, the question is it okay for me to do this rounding or not? And whether it's okay depends on what the answer choices are. Because if the answer choices look like this, if the answer choices were like A, B, C, and D, and if the answer choices were like 9, 10, 12, 14, then this is okay to do because there's really only one choice that is aligning that could be possible with this, right? But if the answer choices were more like 13, 14, 15, now it's not so clear cut. It's not so clear cut what our rounding would have taken us to. Would it, if we punch it into a calculator, will it be closer to 13 or will it be closer to 14 or will it be closer to 15? And so the MCAT is typically going to give you something more along the lines of this, where two of them will be wrong, but your gross estimation is not going to help you decide between the last two. So we need to be a little bit more specific and targeted with our estimating. So how do we do that? So here we have 6. So instead of rounding to a whole number, we can round to the tens place, right? So we could say 6.8, right? 6.8 times, and now with this one, 2.2, this is a 5, right? We could go up to 2.3, or we could go down to 2.2. And the question is, which one should we do, right? The question is, what should we do? And here's the important part. With 6.84, right? If we round 6.84 to 6.8, are we rounding that number up or down? 6.84 to 6.8. We rounded this down, right? If we rounded this down, should we round our other number up or down? This is an interesting question. Should we round, if we rounded down already, should we round down a second time or should we round up? So this is an interesting idea, right? So let's think about it. What if we round down, right? And we have these examples here. We have a 2.3 and we have a 2.2, right? So in this case, we rounded down, and in this case, we rounded up. And what do we actually get from the answers? When we multiply, so this is a down down, and this is a down up, right? By doing this, we get 14.96, or basically 15. And by doing this one, we get 15.6. This is the actual answer, 15.4, right? What is the difference? Between 15 and 15.4, there's a 0.4 difference. Between 15.6 and 15.4, there's only a 0.2 difference. So which was the more accurate rounding? Rounding up or rounding down? Rounding up was the more accurate rounding. So in this way, you see that it's actually, we want to counterbalance how we round. So this is something that might be unintuitive. If we round down twice, we are rounding away from the true value twice. Do you see how this is, you're doubling the effect of your rounding? Whereas if you round down once and then you round up once, you're not straying, right? You're counterbalancing the effect of your rounding. So this is why I said this is a skill that you're probably going to be unfamiliar with, because nobody, told you to round in school, right? Because you had a calculator. So this is something that's very valuable. Even this small choice, right? Even the small choice of round up or down can have a significant impact on the choice, on the answer you choose. Because what if the answer choices were like 15.4, 15.2, and 15.6, right? If they were that close, this has a major impact, right? Because we're not able to multiply 6.84 times 2.25. You could do it out, but it would take longer than just rounding and getting to this. So that's the first lesson with rounding. Any questions about that? Okay, cool. So this rounding, that's how we did with multiplication, right? Now with division, we do it, it's basically the same, but a little bit different. So in division, to keep the numbers proportional to each other, both the dividend and the divisor should be shifted in similar directions. So this is where we want to actually stay consistent. For example, we were dividing 19.5 by 4.67. So we'll put 19.58 by 4.67. Okay, what is the nicest thing that we can do to this, right? This is impossible to solve mentally, right? But if we turn it into whole numbers, we can make it a little nicer. So if we turn 19 into 20, right, we bumped up. Should 4.6 go down to 4 or up to 5? In the case of division, we should go in similar directions. So we bump this up to 5. And then we have 20 divided by 5, which is lovely. Then we have our 4, right? And what is the actual answer for 19.58 divided by 4.67? The actual is 4.19, right? So this is how we want to do that. This is nice. So again, with multiplication, you want to go the opposite way, one down, one up. For division, you want to go both up or both down when we're rounding. Now let's look at an example problem. So here's where we're going to do a lot of problem solving today, just so you guys have a lot of examples of how to actually use this, for real. So here's our first example. A student adds 6.19 grams of solid hydrochloric acid to 0.05 liters of water. What is the molarity of the resulting solution? When I used to see problems like this, it would make my head hurt because I would have a hard time understanding like what they wanted, and like I felt like I was always missing something, right? So to avoid that happening, I kind of follow a formula or an algorithm of specific steps that I always do, so I never make a silly mistake like that. The very first step that I follow is I identify what they gave me, and I identify what I want to get. So I define that as my given and my get. So in this case, what have I been given? So I'll just write on the left my givens. So in this case, I was given that a student added 6.19 grams of HCl, okay? And they gave me that they added it to 0.05 liters of water, okay? And what they want me to get is the molarity of the solution, of the HCl in the water. So now I need to identify, the easiest way to do this is to identify what are the units that I'm dealing with. I've been given grams and I've been given liters. And what is the unit of what they want me to get? Molarity. Anybody know what molarity is in terms of units? Moles per liter, right. Now here we see there's a disconnect. I have been given grams in liters, but I need to get moles per liters. Aha. So now that lets me think about, okay, how do I go from my given to my get, right? If I have grams and liters, how do I get to moles per liter, right? And it might be easier if we start writing it out and seeing. So I've been given 6.19 grams of HCl, and I've also been given well, so what can I so in this case, right, the question is, and I need to eventually get to moles per liter, right? Some amount of moles per liter. I don't know what it is. Some amount of moles per liter. If I want this to happen, right, my liters, right, I see in what I want to get, my liters are in the denominator. I see that. So therefore, I know that this value needs to be in the denominator. So I'm going to write this as 1 over 0.05 liters of H2O, because I see that I need my liters to be in the denominator. Okay, now the question is, I need moles in the numerator. So essentially my job is to figure out what is going to allow me to put moles in the numerator here. And so I know that I need to get moles in the numerator, but I also see that something is missing from here, right? What's missing from here? Grams. I don't have grams in the end. So that tells me what I need to do is figure out a way to turn these grams into moles. So if I put grams on the bottom here, I can divide by grams HCl, right? And I can get my moles of HCl. So in this way, I've kind of, reverse engineered what I need to do. I know that I need to get rid of my grams and get to moles. I know that my liters are here, so that's fine. And now I have my moles here, and that's fine. So this is the structure of my equation. The question is, what are the values that go in here, right? What are the values that go in here? And so does anybody know how to convert between mass and molar mass? Where would we find that information? Yes, indeed, the periodic table. So let's go look up the periodic table. And definitely whenever you're doing this, look up specifically the MCAT periodic table, because this is the one that will be given to you. So this is the info. You don't get any less info than this when you're taking it. So just practice with the one that's been given. So here's our MCAT periodic table. And so what do we want to do? Oh, what happened? Just a sec. Well, in any case, hold on. Let's solve this first. So we're doing HCl, right? HCl. So we have hydrogen and chlorine, right? And H is 1, and chlorine is 35.5. So 35.5, remember, we're talking about rounding. Let's turn this into 36. And this is 1, so 37, right? So then our grams of HCl is 37 for 1 mole of HCl. Okay, one moment. Okay, so we said that the HCl is about where were we at? So in the periodic table, right, we have 35.5, right? And then 1, so 36.5, right? And so 36.5, again, we have the question of how should we round, right? 36.5. Should we round this up or should we round this down, right? And what we can do is look at, this is now we're getting into more advanced rounding. You can manipulate the numbers the way that works the best for you. So let's look at our equation. We have 6.19 times or divided by 0.05, then divided by 36.5, right? 36.5, which could be, let me just get rid of this. It's 36.5. And that could either be a 37 or it could be a regular 36. Now, given the numbers that we have in this equation, the question is, would you rather have a 36 here or would you rather have a 37? And you might be wondering, like, how do I answer that question, right? What would tell me if I want a 36 or if I want a 37? And what tells you that is based on how easy it is to deal with that number. So what I'm noticing is I have a 6 over here, right? And if I have a 6 essentially being divided by a 36 versus a 6 being divided by a 37, which one would you guys rather have? The 36, right? Because it's simplified, it's a multiple. So this is the kind of thing that is a small decision but has a big impact, right? And that's why I want you guys to always set it up first. Set it up first so you can see the links. This is what we mean by critical thinking, at least in the chemistry and physics section. This is critical thinking. This is a decision that you're making that has a lot of impact. And so we see that because we choose to round down here, right? Because we choose to round down here, and this is also a division. Look, because our original value is 6.19 divided by 36.5, right? But I don't want to deal with a 19, and I don't want to deal with the 0.5. So if I round this down to 36, it's a division. I can stay consistent and also round this down. Boom, I have nice whole numbers that are going to work because I rounded both of them down. So it's okay. I'm being consistent with my rounding. So therefore, now we have 6 divided by 36, right? So let's clean this up a little bit. I'm just going to write it above. When I do my 6 divided by my 36, I'm going to get, 1 over 6, right? My grams of HCl and my grams of HCl have canceled out. So that's 1 over 6 moles of HCl. But we still have our liters, right? Our 1 over 0.05 liters of HCl, or H2O rather, is going to give us, what we want, the moles of over liters. Now, here we have an issue. We have a fraction and we have a decimal. That is not the best. We want to be consistent. We either want decimals and decimals, or we want fractions and fractions, right? That's going to help us get the most efficient answers and solve it. So what is 1/6 as a decimal? 1/6 as a decimal is 0.16. I'm not the biggest fan of that. because we've already rounded this, I don't want to turn it into 0.16 and then turn it into 0.15 again. Then we're rounding a lot, right? What I would rather do is turn this into a fraction, because it's essentially, right? And you might be thinking like, okay, I'm not, off the top of my head, I don't know what 0.05 is as a fraction. Okay, that's fine. Do you know what 0.5 is as a fraction? What's 0.5 as a fraction? A half. So therefore 0.05, if we move the decimal 1 over here, right, we're adding a 0. So therefore to the denominator, we add a 0. So in this way, you're going to get very, very used to manipulating zeros and manipulating like the decimal. So this is one way to see, okay, if I know the regular value, like 1 over 4, right? You could do this with anything. So essentially, right, this is going to allow us to easily convert a decimal into a fraction. So now we're seeing that we have 1 over 6 times 1 over, we're going to get rid of the decimal form, and we're going to say it's 1 over 20, right? But this is a 1 over 1 over 20, right? So when we have a fraction in the denominator, we can just flip it, right? And we get the reciprocal. So this is now going to be, this whole thing is just going to simplify into 20, right? Because we flip it. So I'm just going to get rid of this whole thing, and we're going to call it a 20. So that's giving me 20 over 6. 20 over 6 overall. Does that make sense? Because we have 20 over 6. So 20 over 6. So how many times does 6 go into 20? 6 over 6, 6 to 12, 6, 3, 18. Right? So I have 18. So I have 3 going in whole. And then I have 18, 19, 20. So I have 2 left over. 3 and 2 6. What's 2 6? 2 6 is 1/3. So 3 and 1/3. What is 1/3 as a decimal? 3.33. 3.33 what? 3.33 moles of HCl per liter. Remember, we already set up our final unit, right? So we already know that what we've solved for has to be correct. And so that brings us to the final answer of 3.33 molarity, HCl, moles per liter. So this would be a very trivial problem if we had a calculator. We just punch in everything. But because we don't have a calculator, we have to make some very careful and elegant roundings. Okay, and we have to be very elegant about how we solve the problem. Any question and how we set up the problem in the first place. So any questions or any comments or anything about how we did this? The most important thing I want you to take note of is how we rounded the 36.5, and taking note of what is the best number that I have to work with this. That's the key skill that you're going to want to learn. Okay, if that makes sense, we're going to move on to logs. So logs is like basically everything that we've learned so far, but like an extra layer of not complexity, but I think a little bit of unfamiliarness, because we don't use that much, like we don't manipulate logs as much as we manipulate regular numbers. So we're gonna go through logs from the start. So first things, we have some rules that we gotta be aware of. First off, we have what is a log, right? And I always think of it as this thing is raised to this power to get this. That's how I think of it. So if we did, log base 10 of 100 equals 2. This guy is raised to this power to give this number. That's basically how I think of a log, right? So the log of 1 is always 0, because x raised to 0 will always give you 1. the log of this to the log of x to the 1 is just x, right? Anything raised to 1 is just itself. And there are some other rules where if the base of the log is the same and there are two numbers being multiplied, you can separate it into individual logs that are being added. If they're being divided, you can separate them into individual logs being subtracted. Okay, so this is the first part of logs. Now, logs are very, very important in chemistry because we have P. We have P. So you've heard of pH. You've heard of pKa, right? The P here means something very specific. It means negative log. So pH is negative log of H. POH, negative log of OH. Okay? So let's see how we use P. There's also the natural log, which you see sometimes. It's just the natural log is basically just the same thing as regular log, except ln means log base E. Again, we don't have a calculator, so this is not that common. And when you see this, it's like in a very specific and obvious way. It's not, you wouldn't be able to solve for log base E. Decibels, I guess they're just showing you where you would see this. You would also see this in physics with sound. You would see log. So this is the equation for intensity. That's where you see a log. But this is the more common one, the Henderson-Hasselbalch equation, right? So the Henderson-Hasselbalch equation is allowing us to do buffer calculations, right? Because we have the pH and we have the dissociation constant, and then we have the ratio of acid to conjugate base, right? So let's work through a problem here. The pH of a solution of HF, hydrofluoric acid, which is pKa 3.2, is 4.8. What is the ratio of acid to conjugate base in the hydrofluoric acid solution? Okay, so again, let's start with what we have been given and what we want to get. So what have we been given? We've been given the pH is 4.8. So we have the pH. We've been given the pKa is 3.2. So we have the pKa. And then the ratio of acid to conjugate base. So they're just talking about the ratio here, right? So how do we solve for this? Well, first things first, let's get what we want on one side. So if we do that, we'll have, I'll just write on the right here. So first we're starting with, so first I'm going to subtract pKa from both sides and get it over here. So we're going to have pH minus pKa is equal to log A minus over HA. Okay? And now we can plug in the values, right? So the pH is 4.8 and the pKa is 3.2 is equal to log A minus over HA. Okay. And so now we can subtract this, right? 4.8 minus 3.2 gives us 1.6 equals log A minus over HA, right? Now, here's an important question. Did I set up this equation properly? Remember that I'm inputting what I'm given for what I want to get. Is what I want to get here? Where is it? What do I want to get out of this equation? What am I trying to solve for? According to the problem here, right? What do I want to get? The ratio. The ratio of what? the ratio of what are they asking for? A over HA. Are they asking for A over HA? Acid to base, we need to flip. This is important. Acid to conjugate base. A over HA is base to acid. Look at that. Isn't that tricky? Isn't that mean? This is, it's so, that's why I put so much emphasis on what are we getting? What do we need to get? Because you could go through this whole thing and get a number at the end, X number, and you think, oh, good, I solved it. You didn't solve it because you never actually clarified what it is that you're getting, right? This is very tricky. That's why from the beginning, you want to be extremely clear. Am I actually getting what I need to get for this problem? And another thing is, sometimes you might think like, okay, you know what, I'll just do this and then I'll flip it at the end, right? The reason I don't like that is because number one, you might forget. You might forget to flip it, right? Everybody forgets sometimes to flip at the end, right? So that sucks. You don't want to forget. You did all the work, right? You should get the answer correct. Number two, if you set it up properly at the beginning, you don't need to worry about it, right? You can expend all your brain power on just solving it and then know whatever answer I got is correct because I set up the equation properly. And so basically, instead of putting it off towards the end, do it at the beginning. And that's going to make you feel much better about the answers you get, and it's going to, give you the confidence and the security that what you're solving for is actually correct. So exactly like you said, we need to flip this thing first before we actually solve for it. So let's go back a little bit. So the thing that we need to do is flip this, right? And so how do we flip the log? So with the logs, all we need to do is actually multiply by -1. The reason that we can do that is because if we look at the log rule, if we look at our log rule here, right? Right here, this is the one. So we have log of something divided by something, right? So essentially that gives us log a minus subtracted by log HA, right? And so if we multiply this whole thing by a negative, right, we'll be able to flip the whole thing, right? So we'll multiply both sides by negative, and that's going to give us a negative 1.6 is equivalent to a log HA minus A minus. And now we are actually solving for exactly what we want to solve for. Now we're actually solving for what is the ratio of acid to conjugate base. Okay, so that's a very key thing. And now it's just a matter of actually solving it. So to actually solve a log, we can raise both sides. So these guys will both become exponents to tens, since it's a log base 10. So I will say, okay, this 10 here, this is a 10 here, and since I have 10 here and I have a log here, these guys can cancel out essentially. And so 10 to the negative 1.6 would be equal to HA over A minus. Now, depending on what your answer choices are, you might be done or you might not be done, right? Because we don't know, maybe they give you this value. If they give you 10 to the negative 1.6, boom, that's your answer. If they give it to you as a decimal, okay, now it's a little bit trickier. If they give it to you as a decimal, what can we do if they do that? How can we solve for 10 to the negative 1.6 without a calculator? Well, we can't. We can't do this. But what we can do is estimate a range. What we can do is estimate a range. What that means is, I don't know how to solve 10 to the negative 1.6. I don't know. But is there something similar that I do know how to solve? Is there something similar? And so for example, one thing that's similar, if we round this down, we could say 10 to the negative 1. right? What is 10 to the negative 1 as a decimal? And and let me show you how to easily solve this, right? We have 10 to the negative 1, and we have a technique called Lars, or a mnemonic rather. And the Lars mnemonic is, if you move the decimal to the left, you add. If you move the decimal to the right, you subtract. Lars. So how does that work? Well, if I have 10 to the negative 1, I can just multiply anything by a 1, right? So I have 10 to the negative 1, and let me multiply this by a 1. And remember, I'm trying to solve 10 to the negative 1 into a decimal, right? So I'm going to say, okay, I have a decimal here, 1.0 times 10 to the negative 1. And I want to get rid of this. I want to get rid of the 10 factor. So to get rid of this, I can just set the exponent to 0. So how do I get it to 0? Well, if I move the decimal once to the left, I need to add to the exponent. So I'll add plus 1. So by adding plus 1, negative 1 plus 1 is equal to 0. So now I have a 10 to the 0. So I have a 10 to the 0, which simplifies into a 1. And by moving the decimal here, I now have a 0.1. So 0.1 times 1 is just 0.1. So this is telling me that 10 to the negative 1 is equivalent to 0.1. Now, that might have been confusing, so I'm going to do it again with the next value. The other value, I can round this down to 10 to the negative 1, or I can round it up to 10 to the negative 2. And so if I let me solve for 10 to the negative 2 this time. So now I'm solving for 10 to the negative 2, and I want to know what this is as a decimal, right? So I'm going to say, okay, 1.0 times 10 to the negative 2. And my goal is to get rid of this 10 to the negative 2 and just have a decimal, okay? So I know that I need to add 2 here. I need to add 2 to get to 0. To add 2, I need to move the decimal 2 spots to the left. 1, 2. Okay? So that's going to lead this to be 0. That's going to get rid of this whole thing and turn it into a 1. And now I'm left with 0.01. So I know that 10 to the negative 2 is 0.01. And I know that 10 to the negative 1 is just 0.1. Any questions about this strategy? This is very useful. This is like a simple use of this, but this is very useful when you're dealing with lots and lots of scientific notation. Does that make sense so far, though, what I did there? If it doesn't make sense, then I want to show you again. Kinda, yeah. So okay, I'll go through more of them, and hopefully it'll make more sense. But back to the problem that we were working with, right? We're saying that, okay, I need to solve for 10 to the negative 1.6, but I don't know how to solve for 10 to the negative 1.6. So what am I doing? I'm estimating. How am I estimating? I said, okay, I'm going to take a near number, which is 10 to the negative 1, and I'm going to take another near number, which is 10 to the negative 2. And now the cool thing here is that we can say, whatever this value is, I know what it is between. I know that it's going to be less than 0.1, but it will be greater than 0.01. So in this way, I'm able to solve for something that I normally wouldn't be able to solve because it's a multiple choice. So all I need to do is find the answer choice, which falls between this range. So that's the key here, right? So the two important things that we covered here are, number one, how to solve for something that is not solvable mentally. You solve it with a range. That's the first part. The other part was setting up the equation properly, right? They specifically asked for the ratio of acid to conjugate base. So had we solved for this, which is base to conjugate, which is conjugate base over acid, we would get instead 10 to the 1.6. And that would put us on a completely different scale. We would be solving for a completely different scale of answer, and it would be totally wrong. So those are the two important takeaways from this one. Any questions about what we did here so far? And again, this is all recorded, so if you need to go back and look at it, I'm going to put it up on the YouTube later today. Okay, so I'm going to clear this off and we're going forward. And so you see that's essentially what they're saying. We would look for an answer option which lies somewhere between 0.1 and 0.01 and 0.1. That's all we can do in this scenario. Okay. Now, it is ideal to go through and solve as best as you can. If you need to get rid of, but without solving, if you want to get rid of things, you can look at significant figures. You can think about how the magnitude of the value, like whether it makes sense, right? You always want to think about the value that I got. Does it make sense? Does it make sense, like according to what I know? That's a little bit harder to pick up on, but you do pick up on it over time, right? Especially with specific problems. Exponents are super important, right? We're going to be using exponents all the time, especially with powers of 10. So just being very comfortable with all the different exponent manipulations, right? So this is an easy one. Exponents multiplied are just added. Exponents divided are just subtracted. Exponents multiplied, I think this is raising to the power is multiplied, right? So, oh no, so yeah, this is raising to the power, so multiplied. This is that you can distribute the exponent to both the numerator and the denominator. And this is also the really important one, that exponents on the bottom go on top as negative. So you will see this all the time with stuff like this. You're going to see this hundreds of times. How do you solve this? 10 to the 2 will flip up over here, and it will be 10 to the negative 2. And now we're just multiplying these guys. How do you multiply? You add the exponents, right? So 3 plus negative 2 is just 10 to the 1. You're going to do this hundreds of times. Okay, so let's do another problem. Calculate the molarity of 0.424 moles HI, HI in 2.1 liters of aqueous solution, right? So again, we do our same strategy. What have we been given? What do we want to get? So I've been given 0.424 moles of HI. I've been given 2.1 liters of solution, right? And I want to get what? Molarity. So what is our units of molarity again? Moles per liter, right? So this appears to be pretty simple, right? We don't seem to need any kind of conversion. All we have to do is say, okay, 0.424 moles of HI times, and again, so remember, what do we want again at the end? We want moles per liter. So where does my liter need to go? My liter needs to go in the denominator. 2.1 liters times 1. And everything checks out now, right? My moles of HI are in the numerator and stay in the numerator. My leaders are in the denominator and stay in the denominator. I'm good to go. All I need to do is divide these numbers. That's all. So now I'm dealing with 0.42. I'll just write it up here. 0.424 divided by 2.1. Now this is a great example of when I would like to use the Lars technique. I have 0.42 divided by 2.1. I don't like this as much. What would I like more? What would be super easy to solve for right here? I would be very happy. Would you rather be dividing 0.4 by 2 or 4 by 2? Which of these is easier? 4 divided by 2, right? And you might be thinking, okay, but I have a 0.4. I don't have a 4. You can make the 4. You can always just make the nice equation that you want. How do we make it? I know that I need to push this decimal over here to get the 4.2. Okay, pushing a decimal. How am I allowed to do that? Because I can multiply by 10, right? I'm changing by a factor of 10, right? And remember our Lars technique, L-A-R-S. Which direction did I push the decimal? I pushed it to the right. If I push it to the right, I am subtracting from the exponent of my 10. So what I did here was I created the value that I want. And I'm allowed to do it because I'm canceling it out by adding a 10 to the negative 1. Because if we multiply this now, if I were to multiply 10 to the negative 1 times 4, so right now I have what I've created is 4.24 times 10 to the negative 1. Now, if I multiply this out, right, I would say, okay, to get rid of the 10, I need to add 1. To add 1, I move the decimal 1 to the left, right? That will take 10 to 0 and get rid of the 10, and this will give me 0.424, which is exactly what I started with. So therefore, I didn't make any change. All I did was manipulated the number to be easier for me. So this is the power of Lars. You can manipulate things to make it easy for you. So what I did was 10 to the negative 1, right? And now I have a very nice 4.24 divided by 2.1. What is that, right? I can just ignore this. I can just round it down to 4.2, and 4.2 divided by 2.1 is simply 2, right? There's just 4 divided by 2 essentially. So 2, but it's not just 2 because I have this thing. So it's 2 times 10 to the negative 1, right? Now, if this, depending on the answer choices, this might be the answer, or they might be looking for the decimal, right? So how do we solve this as a decimal, right? Again, this is something that you're going to get extremely familiar with. 10 to the negative 1, okay, I need to get rid of the 10 factor. To get rid of the 10 factor, it needs to become 10 to the 0. How do I make it 10 to the 0? I'll add 1 here. Remember, Lars, if I added 1, what direction am I pushing this decimal? To the left or to the right? To the left. So my final answer is going to be pretty much exactly 0.2 molarity HCl, or HI rather. Okay, so you see this is a simple problem if you have a calculator, and it's also simple without a calculator if you just know how to set up the things to make easy eliminations and easy things, right? It's not that this isn't solvable. This is solvable. 0.4 divided by 2 is solvable. It's just it's just way easier to just do 4 over 2. And it might feel like, oh, why would I do all this like times 10 to the stuff? Like, what's the point of all this? It is very, very helpful when you're not just doing this, but you're multiplying by other factors, right? Sometimes you have a conversion chain that is extremely lengthy. So, okay, no worries, Hector. Yeah. So sometimes you have a conversion chain that is extremely lengthy. So you want to be you can keep on top of all the you can keep track of all the numbers and make them easy numbers for you by doing stuff like this. So that's just a little example of that. Any questions so far? So this was it, yeah. Okay, fractions. Fractions is important too. So fractions, right? We know about the least common denominator. You will see fractions on the MCAT. You know about the least common denominator that 2/3 is going to have to become 6/9, right? And 6/9, then you add the numerators and you get 7/9. The tricky part ends up being converting between fractions and decimals. I highly recommend that you learn each of the decimals, each of the decimal conversion. So we know 1/2 is 0.5. We know 1/3 is 0.33. We know 1/4. We know 1/5. 1/6. Do you know it? It's 0.16. 1/7. Do you know it? I think it's 0.14. I'm not sure. 1/8 is 0.125. 1/9. I think it's 0.11. I'm not sure. I think it's 0.11. And then 1/10 is just 0.1, right? I think it's very worth it to know these. I would even know like 1/11 and like maybe 1/12. Sometimes because these you will run into these. It tends to be very difficult to get rid of a 7 or to get rid of a 9 or to get rid of an 11, right? Your options are really to like round or to just turn it into the decimal. So if you know the decimals off the top, it can be very helpful for you to get rid of like a nasty number that you don't that is otherwise hard to shuffle with, if that makes sense. Because like 1/5 is not a bad number because it just turns into 0.2, which is an even number. Very easy to work with, right? You just have to watch out. Some of these numbers are not so easy to work with, and there are only specific ways that you can crunch them down. So multiplication, so adding is obviously like that. Multiplication and division. Multiple. Yes. Okay. So here, so yeah, this is super important, especially with I think we already showed this a little bit, but here we're multiplying these fractions, right? First off, you want to simplify things down as much as possible. Or even if you don't, well, first of all, we could simplify this down to 2/7 times 7/8. 2/7 is a dead end, right? There's nothing we can do except turn it into a decimal. 7/8 is also a dead end, right? We could like round it up to 8/8 and say it's a 1. But before we do that, we want to see, is there anything else we can do? Individually, they are dead ends. But together, they're not dead ends. Together, we see that we can divide the 7s, right? And by dividing the 7s, that makes our life a whole lot easier. Because now we just have a 2/1 times a 1/8. And that gives us a 2/8, which is super easy. Now we have a 1/4. Now we have a 0.25, right? Something that seemed nasty is actually very beautiful. And so this is the key when I'm talking about those big conversion chains, right? Of like moles times grams times liters times whatever. This is exactly what you want to be looking for. You want to look for where can I get rid of these nasty numbers, because you will see something like this. And this 7 over here could cause you problems. But if there's another 7 over here, boom, divide these out. See what I'm saying? If you have 1,000 over here, right? And if you have a 10 over here, boom, divide that out and get rid of a 0 from here. So you make the problems that you want to solve. You're the one in control. You get to match what numbers are going to cancel out with what numbers. That's the beauty of setting up everything at the beginning. And then you get to make the easy eliminations for yourself. Okay, this seems very simple. It is extremely powerful. It is extremely, extremely useful for getting through your problems faster and getting through your problems more accurately. You guys know how to multiply fractions. Just multiply top and bottom. Dividing, right? Dividing would just be, we don't actually divide fractions, we just take the reciprocal and multiply, right? So 1 over 3 divided by 4 over 7 is actually just 1 over 3 times 7 over 4, right? I think that's pretty common. Okay, so let's try a practice problem, right, of this fraction stuff that we're talking about. Yeah. So anybody doing physics have you guys seen the thin lens equation yet? Thin lens equation for optics and stuff. Thin lens equation. So this thin lens equation, right? A common application of fraction math and physics on the MCAT. The thin lens equation is just this. 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance, right? So this is where we're seeing addition of fractions. And so to do this, there's a problem. Okay, so let's see this problem. Suppose a converging lens with a focal length of 4 centimeters is placed 6 centimeters away from an object. Determine whether the object produced by this lens is real or virtual. Okay, what have we been given? What do we want to get, right? So we have our equation up there, and we want to know what were we given out of this equation and what do we want to get. So what were we given? A focal length of 4 centimeters, right? So a focal length is right here. So we're given our focal length. Is placed 6 centimeters away from the object. So we have the object distance as well. We have the focal length and we have the object distance. Determine whether the image produced by this lens is real or virtual. Okay, so this is a little bit of a step further. They're not asking for the image distance, but they're saying, is the image distance, is the image real or virtual? So we're not sure what that means yet, but at the very least, we probably have to solve for the image, right? And then a step further. So first things first, let's do that. So again, remember, we always want to be setting it up so we're solving for what we want to get. In this case, we're saying, okay, let's start by solving for the image distance. So we're going to rewrite the equation such that the image is on one side, right? And then we'll plug in our values, 4 for the focal length and 6 for the object distance. And then this needs to be common denominator, right? So 4 times 6 is 24, 6 times 4 is 24. And then we have 6 over 24 minus 4 over 24. That's giving us 2 over 24. And then we can cross multiply this. So it's going to be cross multiplication is going to give us 2i is equal to 1 times 24. And we just divide both sides by 2. And we get that I is equivalent to 12 centimeters, right? Okay, so 12, right? I is equal to 12 centimeters. Now, this is not your solution, right? This is not the solution because they asked something else. They asked, where is it? They asked, is the image produced by this lens real or virtual? So in this case, they are saying, with this value, we need to be able to make that determination. And with this value, the fact that you need to know to solve this is that if the image distance is positive, the image is real. So that's why we had to solve for the image distance to know, is it positive or negative, right? And in this case, since it's positive, that tells us that the image is real. So this is a little bit of a step further. This is an example of that content knowledge allowing us to get a problem correct, essentially. Okay, so those are the basics of MCAT math, right? We talked about rounding. We talked about setting numbers up to be eliminated better. That's the basics. Any questions about what we covered so far? We're going to use them now in a practice passage. But any questions so far? Is there anything that I should look at again or explain again? Or does everybody, or are you guys just ready for the practice problems? Okay, let's just do some practice problems then. So this is a titration. I used to hate titration stuff, but it's not too bad now. So let's see here. Oh, what? Okay, so Um, and okay, so here, this is a titration, right? Obviously, we see the titration graph. Um, Titration experiment with acetic acid as analyte and sodium hydroxide as titrant. To conduct the experiment, 100 milliliters of 0.2 molar NaOH, 50 milliliters of acetic acid of unknown concentration added to an Erlenmeyer flask and placed beneath the burette. Students were asked to determine the concentration of the provided acetic acid with a pK of 4.7. And we got this titration curve. Okay, let's take a look. Question 1. Approximately how many moles of NaOH were present in the burette at the equivalence point of the student's titration? Okay, so what are we given and what do we need to get? First of all, we need to get moles, right? Another thing I forgot to mention, if you have multiple choice, your given is already in the multiple choice, right? Oh, I can clearly see what I need to get is moles. So I need to set up my equation such that mole is the last unit standing, right? That's clear. So I need to get moles. So I know that I need to get moles. Moles of what? Moles of NaOH. So that's clear. That's what I need to get. But what am I given? What have I been given? Present in the burette at the equivalence point. Okay, so this is one of those things where your content knowledge needs to inform you of what you need to do. Anybody know where the equivalence point is on this graph? pH equals 9, yes. Oh, nice. Perfect. So you guys know, yes, the equivalence point is the midpoint of the steepest region, right? And so right over here is our equivalence point. So how does that help us with this problem? How does that help us with this problem? What is the link? What's the link here? How do we get to moles from there? Right. Right on our x-axis, we have 28 milliliters of 0.2 molar NaOH. Okay, so let's look at that. We have 28 ml times 0.2 molar, and molar is moles of NaOH per liter, right? Okay. Am I done setting up this equation? No. What's missing from this? Mole below the 20, mole below here? You can just unmute and tell me what you're trying to tell me. milliliter to liter conversion, right? That's one important part. We have moles to moles here, that's fine, but we don't have any milliliters here and we don't have any liters here. So we need to get rid of this. So we have a milliliters here and we have a liters here. So that's not going to work. We need to get rid of the milliliters to the liters. So how can we do that? Well, we can say, first of all, I know that my milliliters needs to get rid of, so it needs to be in the denominator. And my liter needs to be above, so it needs to get over here, right? And so, yep, we have our conversion of 1,000 over 1, right? And we've set it up properly now. So now if we can just go through and eliminate the units, and we see that our units work out perfectly. So now it's just a matter of let's solve for these numbers, right? And how do we solve for the numbers in the most efficient way possible? So let's look. We have 28 times 0.2 divided by 100. Okay? Now, I don't like the idea of solving for 28 times 0.2. I would much rather solve for 28 times 2. That's way easier, right? So what do? I will just make that happen for myself. Or I could even do, you know what I could also do? I could, instead of 28, I could just do 2.8 times 2. How could I do that? If I move this to the right and make a 2, I'll move this to the left and make a 2.8. That's totally okay. Essentially what I did was I stole the 10 from 28 and I gave it to 0.2 and I made it 2. So I'm just shuffling around tens. Now I have 2.8 times 2, and 2.8 is easy to multiply. 2.8 is just 5.6, right? 2.8 times 2 is going to give me a 5.6 over 100, right? And so from here, oh, sorry, not 100, 1,000. My bad. Good catch. Not 100, 1,000. 1,000 milliliters. My handwriting is bad. That's the reason. My handwriting is bad. Okay, so now I have 5.6 over 1,000, right? So now the question is what would be the best way to solve this? And so since I have all these numbers in the bottom, what I'd like to do is 28 milliliters. Yeah, 28 milliliters of 0.2 molar. Yeah, so 5.6 times 1 times 10 to the third, right? I can flip this up, 5.6 times 10 to the negative 3, right? And then that is essentially pushing, I can push this to get rid of this, that'll be plus 3, right? To do plus 3, I need to move it to the left, right? So 1, 2, 3. So I'm looking at 0.0056. But this doesn't seem to align with any of our choices. So there must be a mistake here somewhere. So what is the mistake? 1,000 milliliters per 1 liter, that's fine. 28 milliliters. 28 milliliters. It is 28 milliliters for 0.2 molar NaOH. 28 milliliters times 0.2 molar of NaOH, 0.2 moles per liter of NaOH. Yes. The milliliters and mils cross out, the liters and liters cross out, and then we're left with moles and moles. what they wrote before the graph. Perhaps, yeah. Oh, wait a minute, wait a minute. Approximately how many moles of NaOH were present in the burette at the equivalence point? But they already had 100 milliliters of 0.2. Okay. 100 milliliters of 0.2 molar NaOH. So if that's the case, to conduct the experiment, 100 milliliters of 0.2 molar NaOH was added to the burette. So it's probably 128 milliliters and not one. Yeah, since we already started with 100 and they're adding 28, right? Okay, so let's try that. Yeah. So if we're at 128 milliliters, right? And so now let's do the same things that we were doing. Okay, 12.8 times 2 is going to give me 24, 25.6, right? 24 is 16, 25.6 divided by 1,000. Okay, and now if I do 25.6, and then I have essentially 0.025. And this, I guess this is the closest one, 0.0229. I'm not. The question is if this milliliters is being done correctly. To conduct this, 100 milliliters of 0.2 molar NaOH was added to burette, and then present at the equivalence point was another 28 added. Yeah, that's that. I think we've set up the equation properly. I think everything is okay there. The question is just whether the numbers are correct, right? The 1,000 is correct. The 0.2 molar is correct. So if it's 128, then it should be B. That's what I'm assuming. But yeah. Should we look at the answer now or after we solve the other ones? Okay, now, right away, no hesitation. Okay, let's go see. Let's scroll down. Choice C is correct. Okay, hold on, let's see. At the equivalence point, 28 milliliters of NaOH was added to the Erlenmeyer flask, leaving 72 milliliters in the burette. Right, okay. Right. Okay. Dang it. So okay. So this is definitely an example of like we set up everything correctly, but it's just the content knowledge of how a titration works, right? They're asking about the burette, right? So this is a live example of why knowing what you're getting is so important. How many moles were present in the burette at this point of titration, right? In the burette. 100 was added to the burette, but then this 28 added was to the flask, right? Like placed beneath the burette. So the 28 was dripping out of the 100 milliliters. So then the question asked how much is left in the burette. So yeah, unfortunately, so if we drew it out, we started with 100 milliliters up here, and then and then 28 got dripped into here. So there was 28 milliliters here. So there was 100 minus 28, leaving us with 72. Yeah, that's a tough one. That it's purposely unclear wording, right? Because it's like it's purposely because they want you to be able to know like how a titration works. And this is again like these kinds of things you would only pick up through practice of like, okay, I got this titration question wrong because of this. Next time I'll pay very close attention to what amount, what they're talking about, you know? So that's pretty. I think it's good that this happened because we get to see exactly where we went wrong, right? None of the setup is wrong. Only the value is wrong. You were thinking choice C because A and B are too close, and if you're estimating, I can't be bothered to check A. Actually, that's a really good point. That's an extremely good point. A and B are way too close to be this. I don't feel like this would happen on the real MCAT, where they have things that are way like only a 0.001 difference. But that's a good point. These are way too close for one of them to be correct. And these are, although the difference here is somewhat similar, but I guess it's at least different enough that you can make a decision. I don't think that's wrong. I think so let's solve it through with 72 and see how we can round it properly to distinguish between C and D, right? Because C and D are extremely similar, right? So how do we round it properly such that we get the correct answer? So let's see how much I can undo here without losing. Da, 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 da. Okay, no, let me just leave this. Okay, and so now we're going to say that this isn't 28, 28, but this is 72. Okay, and now we're going to be dealing with 72 times 0.2. Again, I'm going to do this thing, and now I have 7.2 times 2, which is just 14.4, and 14.4 divided by 1,000 is 14.4 times 10 to the negative 3, and I can move this 1, 2, 3, and I get 0.0144, aka 0.014. So in this case, you see how important it is to not get to not round actually, because if we round this to 7, well, actually, even if we round it to 7, it's okay because we'll still get 0.14. So as long as you have the number correct, you wouldn't end up with D. You would always end up with C. So in this case, it was actually a content issue, not a problem solving issue. How we solve it is correct. It's just missing this part with the 72 rather than the 28. But that's a good one. That's a good one. Any questions about this one so far? Okay, let's check out the next one. How many grams of NaOH were added to 100 milliliters of water to create the solution used in the titration? So what is the solution used in the titration? 0.2 molar NaOH. Let's just double check, right? 100 milliliters of 0.2 molar NaOH. Okay, so, and 100 liters of water. So we're dealing with and to create the solution using the titration. So 0.2 moles per liter of NaOH. And to create this, we started with 100 milliliters of water. Okay, that's what we've been given. Times what else, right? So now the question, so we're starting with 100 milliliters. Again, we have this liter to milliliter issue, right? So we got to get rid of the milliliters. And now, oh, no. Okay, look, this is really important, right? I'm setting it up like this, right? And now I'm running into an issue. If I do this, I'm going to end up with liters at the top. I'm not supposed to get liters at the top. I'm supposed to get liters at the bottom, right? So that tells me that I set this up wrong already. So that tells me, working backwards, that I need to have I need to have 1,000 milliliters up here, and I need to have 1 liter down here, so that the 1 liter will go to here. So that tells me that where my milliliters are right now is wrong, and that I should instead have 1 over 100 milliliters times 1,000 milliliters over 1 liter. Now everything is in sync, right? Now we're in sync. Now we're going to get the 1 liter that we want. Okay, that's really important. We want all of the setup to be perfect at the beginning. So it allows us to go back and see if we make a mistake with our numbers, we can see very clearly what the culprit is, right? Now, moles. We have a moles issue. Okay, what do we do? And we also want grams, right? Or rather, oh, yeah, we have to figure out how many grams of NaOH. Oh, hold on, wait a second. How many grams of NaOH were added? So actually what we're solving for is grams. So if we're solving for grams of NaOH, then, so it's some amount of grams of NaOH times some amount of grams of NaOH, and then we obviously need to convert grams to moles, right? To moles of NaOH. Some amount of grams of NaOH to moles of NaOH. How many grams of NaOH were added or equal to, right? Well, liters, moles. Oh, okay, I got it. So, grams of NaOH. Working backwards. Grams of NaOH started with, so we have our 0.2 moles NaOH per liter, right? Now we have our 1 liter per 1,000 milliliters times 100 milliliters. Okay, so this is how now that we've correctly identified what we need to get, right? The grams of NaOH, what we've been given was the 100 milliliters, and what we were given was the 0.2 moles of NaOH. Boom. Okay, now this is, okay, but no, we're not done yet, because milliliters times milliliters, 1 liter times liter, moles is not grams yet, right? So over here, we would also have times some amount of moles to some amount of grams. Okay, and that would be the molar mass. So we can go to the periodic table, and we can see that NaOH is going to be 23 plus 16 plus 1. So 23 plus 1 is 24, plus 16 is 40. So we're getting that 40 grams per 1 mole of NaOH. Okay, so now we have our complete setup is equal to some grams of NaOH. And now that we have a complete setup, it's easy to manipulate these numbers. 100 divided by 1,000, okay, that's just going to be 10 at the bottom. Or we could do something else. If I have a 0.2 and I want to make it a 2, right, I could say, okay, 10 here and 2 here, right? I could do that. I can move the decimal over here to the left and move the decimal over here to the right. So now I have a 10 and a 2. Okay, I'm happy with that. I have a 2 times a 40. Okay, that's going to be an 80, right? 2 times a 40, that gives me an 80. 80 times a 10, that gives me 800. 800 divided by 1,000, okay, 8 over 10. 8 over 10, that's just 0.8. 0.8 grams, 0.8 grams. So the setup is really the hard part here. And then after the setup, you just manipulate the numbers however you want, whatever makes sense to you, right? But the point, the hard part here is figuring out, okay, what am I supposed to get, the grams, and then how do I get to that? How do I string it along to get to the point where I'm outputting grams? And doing this all at the beginning is important so that whatever value you get, you know it is in the unit that you want. So you do all the setup at the beginning in order to get the exact value that you want. And you know without question that what you just solved for is grams. And that's what you do there. Okay. You have a question? Yeah, go ahead.
Yeah, so I just wanted to see if the way that I did it in my head was would be incorrect or if it would work for any situation like this.
Mm-hmm.
So like I'm kind of lazy, so I kind of look for the easiest way to do it. So what I did is when I saw we need grams, I just checked what the molar mass is, and then I saw it was 40, and then I know it's 2 molar, so that's 2 moles for every liter. So I know it's going to be some multiple of 8, and then I just look for something that had 8 in it.
I mean, you are thinking, like, that's not wrong. You because what you did in your head is essentially like linking the 8 to the 40, right? Which is exactly what we did on paper. The only part where that would trip you up is like conversions between like milliliters and you're not accounting for the milliliters there, right?
Hmm.
You're just accounting for, it's supposed to be some multiple of 8. The other thing that might trip you up there is if it was a number that wasn't like 0.2, where if it wasn't where it wasn't going to be like a neat multiple of 8. If there was like a 3 or a 7 involved, if that makes sense.
Got it.
Right? I mean, I'm not saying that's not wrong. Like that's a good way. Like you're thinking ahead in terms of like what you're doing is thinking about like, does my answer make sense? Which is really good, right? Does the answer I get make sense in terms of what I think it should be? Which is good. And in fact, I would say like that's one of my weak strengths, my weak points of like, does this make sense? So that's why I do this style where I'm just making sure to account for everything so that I don't, because I don't always like account for the fact of, does this make sense? So I just do this so that I know whatever I get has to be correct.
Got it. That makes sense. Okay, thank
Yeah.
you.
Yeah, no problem. But everybody is going to have like a different, like once you find your niche of like what makes sense to you, do that, because that's going to be more unique to you and more sensible for you. But I guess like there, just to bring psychology into this for a quick second, um, what I'm doing is more of an algorithm. What you're doing is more of a heuristic. Does that make sense? Did you study psych yet?
Nah, I don't have any clue exactly what
Okay,
that is at all.
okay. An algorithm is something that's a little bit more labor intensive, but it goes through all the steps and it gets you the correct answer every time. A heuristic is a mental shortcut, which could be error prone, but is better than nothing. So that's your quick psych lesson
Yeah,
of the difference between what we're doing.
yeah, that definitely does make sense.
Yeah, and now you won't forget those. Now when you run into algorithms and heuristics, you'll know what we're talking about. Okay, so let's keep going. What is the approximate ratio of HA to A minus at the equivalence point of the titration? So we go back to, at the equivalence point of the titration, we're at pH 9. This is again Henderson-Hasselbalch, right? So let's just go back and grab the Henderson-Hasselbalch equation. Boom, boom, boom. Right? And we got pH equals pKa plus log A minus over HA, right? And so we scroll down. And we'll come here. Okay, what is the approximate ratio of HA to A at the equivalence point of titration? And so what did they give us so far? They gave us the pKa, that's good, and they gave us the pH as well, because they said at the equivalence point of titration. And at the equivalence point, the pH was 9, right? So they gave us the pH of 9. They gave us the pKa of, what was it? 4.7. Okay. All right. And so we want to isolate what we want on one side, right? The ratio. So 9, I can just move pKa to the left side, subtract from both sides. So 9 minus 4.7 is going to give me 4.3, right? 4.75, yeah, 4.3 is equal to log A minus over HA. Is this set up correctly to get what I want? What am I trying to solve for? Yeah, you want the opposite, right? What is the approximate ratio of HA over A? And what I have here is A minus over HA. So I always want to set it up so that whatever value it spits out is going to be exactly what I want. No thinking after that. I need to set it up properly first. So I'm going to, before I log both sides, I need to invert the ratio, right? So to invert the ratio with a log, I can just multiply by -1. So that's going to give me a -4.3 is equivalent to log HA over A minus. Now I'm good to go. Now whatever value I solve for is going to be exactly what I want. So I'm free to do what I want. So now to get rid of the logs, I'm gonna, like you said, I will remove the log from both sides by raising everything to 10. So I'm just going to move up here for a second. So that's going to give me 10 to the -4.3 is equivalent to the log and the 10 cancels out, and I get HA over A minus, right? And that gives me the answer. Now, you see the danger of what if you did not make sure of what you were getting, right? If you didn't, if you said, oh, this looks good, and you went through this without multiplying by -1, at the end you would have gotten 10.43 is equal to A minus over HA. And if you weren't paying close attention, you would have said, oh, okay, B is the correct answer, right? So it's just useful to, at the start, make sure you're solving for what you want, and then boom, like, okay, whatever I got is clearly what I want because I put in the time to make sure that I was solving for what I needed to get. So that's important. Now, by how many orders of magnitude is the concentration of acetic acid after the student has added 14 milliliters of NaOH greater than the concentration of acetic acid after the student has added 28 milliliters? So we need to look at the concentration of acid, difference between 14 milliliters and difference between 28 milliliters. So if you look up at 14 milliliters, this is basically 0, 1, 2. It's at 2 pH, and at 28, it's at 9 pH. So what is the difference in order of magnitude between pH 2 and pH 9 is essentially what this question is asking. Between pH 2 and between pH 9. They're asking for orders of magnitude of concentration of acid. First of all, between 9 and 2, what's the difference in value? How many, what's the difference? 9 minus 2. 7, right? So right away, we're not dealing with A or B, right? It's either 10 to the 7 or 7, right? That's a safe assumption to make. Now the question is, how many orders of magnitude is the concentration of acetic acid, right? If they're asking about protons itself, right, in terms of concentration of protons, the difference between each pH, right, is times 10, right, or 10 to the 1 between each pH. So between the difference between pH 2 and pH 9 is going to be 10 to the 7, right? But this is asking, this is why we always have to think about what are we being asked for? What do we want to get? This is not asking for the difference in the protons or the difference of, this is not asking for the exact value of the concentration difference. This is asking for the orders of magnitude. And the orders of magnitude specifically is referring to this value, the 7. So in this case, it should be this. If it asks for the exact concentration difference, it's 10 to the 7. If it asks for the order of magnitude, it's asking how many times do we multiply by 10? That's essentially what orders of magnitude is mean. And in this case, it's just 7. So this isn't anything that we're solving for. This is just a terminology thing of what does orders of magnitude mean. And the last one, assume that instead of acetic acid, formic acid, pKa 3.7, of the same concentration was used in the experiment. How would this affect the pH of the equivalence point? Oh, this is a good question. Okay, this is a cool question. This is asking you like your understanding of titration, right? So assume that instead of acetic acid, so let's go back and look at acetic acid, pKa 4.7, okay? And instead of that one, we're now using a pKa 3.7. How does this affect the pH of the equivalence point? Okay, let's go back and look at this. pKa 4.7 was the original. Now we're being asked to think about pKa of 3.7. If we had a pKa of 3.7, what would happen to the graph? And our choice, or what would happen to the equivalence point? And our choices are essentially that it would increase, or it would decrease, or there would be no change, or it would increase or not have any change. So essentially we're thinking about increase, decrease, or no change, right? So what do you guys think? What is the significance of pKa and how would it affect the pH? First of all, let's talk about pKa. What is pKa? If the pKa is smaller, isn't it a weaker acid? If the pKa is smaller, isn't it a weaker acid? How do you know that? What is Ka? Right, it's a constant thing, right? So let's not confuse pKa and Ka, right? Let's solve this right now. First of all, what is Ka? Right? What is Ka? What is that? Acid dissociation constant. Exactly, right? Acid dissociation constant. Sorry, please excuse my horrible handwriting. I should have just written it with text. acid, let's just call it acid dissociation constant. Okay, Ka. Now, what is P? We talked about what P means in context of chemistry, right? We know that H plus is just the concentration of acid. And so then what is pH, right? Negative log, exactly, negative log of H plus. So in this case, P is adding a negative log. Right. So this, by thinking about what P actually means, it informs you the relationship, right? So now let's think about, and this is what you should always do. Start with the idea that you know, and then convert it. So I know my content knowledge is that that an increased Ka is a stronger acid, right? Because I know that Ka is my acid dissociation constant. That's the fact that I learned and I memorized. Okay. How does Ka link to pKa? Well, if it's a negative P log, that means that an increased Ka is going to link to a decreased pKa if it's negative log, right? And that's telling us as pKa decreases, acid strength increases. By linking these two, by linking the Ka and the pKa, we get to see the relationship between pKa and acid strength as well, because we know the relationship between Ka and acid strength. So back to this question. Now we see that our pKa has decreased. Now we know that because we know how Ka relates to acid strength, we know that pKa decrease will give us a stronger acid. Okay. Finally, if we have a stronger acid, what would happen to pH? Would pH increase or would pH decrease? Right. Therefore, the equivalence point would slightly decrease because you have a stronger acid. And ultimately, that is the answer there. The equivalent point would decrease. So the key here is relationships. This is just starting in chemistry, but this becomes extremely important in biology and biochemistry. This is how you relate things and you don't get confused, right? Getting confused is the worst part because you know all these things, but it's like, okay, Ka, pK, which one goes up, which one goes down? You don't want to confuse yourself. You need to write out these relationships so that you keep track and you don't flip them around. Okay? So because all it takes is one flip to be completely wrong, right? All it takes is one flip. Think about this. If I said, okay, I think increased Ka is a weaker acid, you got this whole question wrong now. You just get the whole question wrong because that one fact is wrong, right? If you said, just like at the beginning, we thought, oh, maybe decreased pKa means a weaker acid, right? It's all wrong now. So what we need to know is one fact very strongly, and with that strong content knowledge, we can infer other relationships. So that's essentially what we're going to do more so next week. We'll go over some biology and biochemistry, and we'll look at how we use those relationships and we exploit those relationships. By knowing some relationships really well, we can infer the relationships that we don't know that well. Okay, so that was a good ending. That links back to like what we're gonna do soon. But overall, I think everything was okay. The first one threw us for a loop because of the 72, but again, that's content knowledge. I think everything else, 0.8, that's right. Negative 4.3, that's right. Choice D, the ratio we got. Choice B, yeah. Okay, so that was it for this session. We went over MCAT math, we went over rounding and all that. And next week, so let me just see here.